The seafloor off the coast of Oregon is rising, not metaphorically, not over a distant geological timescale measured in centuries or millennia. Right now, nearly a mile beneath the Pacific Ocean, the crust is lifting upward under measurable pressure. Instruments anchored directly to the seabed are detecting the change in real time. And the most striking detail is this: the summit of Axial Seamount has already risen higher than it stood in the hours before its last eruption in 2015. That is not speculation. It is not interpretation. It is a direct physical measurement of deformation occurring beneath thousands of feet of water. Axial Seamount sits roughly 480 kilometers offshore and about 1,500 meters below the ocean surface. It is inflating faster than at any comparable stage since the previous eruption cycle. But what makes this moment different from every inflation episode before, it is not just the magnitude of the uplift. It is the fact that scientists are no longer simply observing the buildup. They are forecasting it. For the first time in the history of volcanology, an eruption forecast is being tested prospectively in real time. Data is streaming continuously from a dense network of seafloor instruments, and the prediction is being published before the outcome is known. If the forecast holds, it could represent one of the clearest demonstrations that eruption prediction can move from retrospective explanation to forward-looking science. If it fails, it will reveal exactly where the limits of our current understanding still lie. Either way, what is happening beneath the Pacific right now extends far beyond a single submarine volcano. Axial Seamount rises more than 1,100 meters above the surrounding Juan de Fuca Ridge, a spreading center where tectonic plates pull apart. As the plates diverge, decompression melting in the mantle generates basaltic magma that rises upward to form new ocean crust. Over hundreds of thousands of years, repeated eruptions have built a broad shield volcano, gradually constructing a rectangular caldera at its summit approximately 3 kilometers wide and 8 kilometers long. That caldera is not a random feature. It is the physical record of repeated structural collapse events, each one marking a previous eruption cycle. Axial follows a rhythm. It inflates as magma accumulates beneath the crust. It fractures as pressure builds. It erupts when structural failure occurs. The caldera floor drops as the magma chamber drains. Then the system begins loading again. This cycle has repeated for centuries. Geological reconstructions suggest roughly 50 eruptions in the past 800 years. In the modern monitoring era, Axial erupted in 1998, 2011, and 2015. Each eruption followed a remarkably consistent sequence of deformation, seismicity, and collapse. Months before each eruption, the caldera floor began rising measurably. Seismicity increased as magma forced open fractures in the brittle crust overhead. Thousands of micro-earthquakes swarmed beneath the summit. Then, often within a matter of hours, the system crossed a mechanical threshold. Fissures opened across the caldera. Lava erupted in glowing sheets, spreading across the seafloor at temperatures exceeding 1,000 degrees Celsius. As magma drained from the chamber below, the caldera floor subsided. In 1998, it dropped nearly 3 meters. In 2011, about 2.5 meters. In 2015, roughly 2.1 meters. The collapse was abrupt and detectable across vast distances. Hydrophones recorded implosion signals that propagated across the northeast Pacific basin. The ocean itself carried the acoustic signature of structural failure. After each eruption, something equally dramatic occurred. Hydrothermal systems reignited along the caldera walls. Superheated mineral-rich fluids surged through fractures in the rock. Snowblower vents released plumes of white microbial material into the water column. Within days, new ecosystems began forming on freshly solidified basalt. Axial does not simply erupt and fall silent. It resets its environment. Following the 2015 eruption, scientists believed they understood the rhythm well enough to forecast the next event. Inflation resumed. The caldera floor began rising again. Based on previous intervals, researchers projected another eruption around 2025. But 2025 passed without failure. Inflation reached levels comparable to pre-2015 conditions. Yet the crust did not break. That non-eruption became one of the most informative moments in the entire experiment. It revealed that inflation alone does not define the eruption threshold. The missing variable was sustained seismicity. In 2015, earthquake rates surged past 2,000 events per day during the final buildup phase. In 2025, uplift increased, but seismicity did not sustain that intensity. The system was loaded, but not critically loaded. The crust was stressed, but not yet at failure. The model had to change. Now, the signals are shifting again. According to William Chadwick at Oregon State University, The average differential inflation rate has nearly doubled in recent months compared to much of the post-2015 recovery period. The caldera floor is rising at approximately 10 centimeters per year. More significant than the absolute number is the acceleration of that rate. In mechanical systems, acceleration often precedes structural failure. Seismicity is increasing as well. Current earthquake counts average in the hundreds per day, with periodic spikes exceeding 1,000. While still below the sustained swarm levels observed immediately before 2015, the upward trend is clear. To move beyond simple pattern matching, researchers implemented a physics-based failure model developed by teams at Uppsala University and ETH Zurich. This model does not simply compare present deformation levels to past thresholds. It analyzes the interaction between uplift and seismic release. It measures how elastic strain energy accumulates within the crust. It tracks how fracture frequency accelerates as stress approaches a breaking point. It examines the curvature of the system's trajectory toward instability. This phenomenon is known as critical point behavior. It is the mathematical signature that systems display in the final stage before structural collapse. Landslides exhibit it before slope failure. Glaciers exhibit it before calving events. Rock masses exhibit it before rupture. Volcanic systems exhibit it before eruption. Retrospective testing demonstrated that this model could successfully reconstruct the timing of previous axial eruptions using archived data. Now it runs forward in real time. Each forecast update is time-stamped and archived before the eruption occurs. The experiment is transparent by design. If the eruption occurs within the projected mid to late 2026 window, the validation will be measurable. If it does not, the discrepancy will refine the science further. Forecast windows are not guarantees. They are probability ranges, but the probability curve is tightening. If axial erupts within the projected window, the sequence will unfold quickly. Earthquake swarms will intensify as fractures propagate through the brittle crust. Magma will exploit those fractures, erupting through linear fissures extending kilometers across the caldera floor. Lava will spread outward in glowing sheets, reshaping the deep ocean topography. The caldera floor will drop, potentially by 2 meters or more, as support drains from below. Hydrophones will record the implosion associated with structural collapse. Within days, hydrothermal vents will surge back to life, releasing superheated fluids and fueling microbial blooms across newly formed basalt. For the first time in history, the entire sequence will be recorded in real time by a dense network of instruments. There is no meaningful tsunami risk from a standard eruption sequence at Axial. The 1,500-meter water column above the caldera absorbs and dissipates eruptive energy. Seismic waves attenuate before reaching land at damaging levels. Coastal communities are not in danger. The stakes are not about human safety. They are about scientific precision. If Axial erupts within the forecast window, it will demonstrate that eruption forecasting can move from retrospective reconstruction to predictive science grounded in physics. It would mark a turning point in volcanology. For decades, eruption forecasting has relied primarily on probabilistic assessment and pattern recognition. Axial represents a different approach. Here, the forecast is published before the outcome. The model's performance will be evaluated prospectively. If the prediction succeeds, it suggests that critical thresholds in volcanic systems can be identified in advance. If it does not, the failure will refine the approach and improve the next forecast. Right now, nearly a mile beneath the Pacific Ocean, magma continues to press upward. The crust is stretching. The inflation rate is accelerating. The earthquake rate is climbing. The instruments remain online. The model continues to run. For most of human history, volcanic eruptions arrived without warning. Axial Seamount may become the first volcano we meet on schedule. The question is not whether it will erupt again. Its geological cycle makes that likely. The question is whether, for the first time, science will cross the threshold before the volcano does.